Okay, so we kind of stopped kind of in the middle of a problem there because these are really two parts of the same problem. Because the second part is referring to the same sample back here. So we originally calculated the number of molecules of HNO3 or nitric acid in this sample where we had the mass. Right, what we want to calculate here is how many oxygen atoms are in this sample. And that would really just involve another step onto the end here of our first calculation. So if we just add on to the end there, so if we look at where we finished, molecules of HNO3 is what we want to cancel out. If I added another step to this previous equation. And I want to compare that to atoms of oxygen. Now, how many atoms of oxygen are in that molecule? That's information that's present in the formula, right? And this one always surprises me, like how many people will get just completely shut down by this type of problem and not realize that those numbers are right there. That's something we've been looking at all along, is what those subscripts are. So the subscripts here are describing 1 hydrogen, 1 nitrogen, 3 oxygens. That's the molecular composition of nitric acid. So there are 3 atoms of oxygen in every molecule. Okay, add that on to the previous calculation, and that would tell us how many atoms of oxygen are in our sample. Now I've still got my previous answer in the calculator, so if I just multiply that by 3, that would give me 1.20 times 10 to the 23rd atoms. So it would still be 3 sig figs, so we'd have to stop at the 0, right? That 0.01, that 1 is no longer present in our sample when we multiply it by 3. Okay? We could easily do that question with, if we did it with how many nitrogen atoms or how many hydrogen atoms, we wouldn't even really need another step because it would be 1 to 1 in terms of the ratio. But you could do something like how many total atoms are in that sample, in which case there's 1 hydrogen, 1 nitrogen, 3 oxygens is 5 atoms. So there's 5 total atoms in each molecule of HNO3. That would be a reasonable problem as well. Okay, moving on to the next page, and there's another issue here on the next page. This also relates to composition of molecules, but it treats it in a way that it turns out to be very useful in terms of something we might want to actually do in a laboratory, which is determine the formula of a particular compound or molecule. So what we're going to do is talk about how we can define percent composition of compounds, but then what we really want to do will come on the next page, where we kind of reverse the process and we use the percent composition to figure out the formula of the molecule. So percent composition, we've talked about percents before. Percent is part over whole. So when we're talking about percent composition, we're talking about the masses of each individual element compared to the mass of the entire molecule. So what we want to calculate here is the percent composition for each element in this compound. So this is iron, titanium, and oxygen. So percent iron would be the mass of iron in the sample divided by the mass of the entire sample. So that would be FeTiO3. Right? Now the mass of the entire sample, that's formula weight or molar mass that we talked about before. We get there by adding up the mass of the iron, the mass of the titanium, the mass of the oxygen. So just calculating formula weight is going to get us all the pieces here. So let me just write this out for the others. The percent titanium would be the mass of titanium divided by the mass of the entire molecule, so FeTiO3. And the percent oxygen would be the mass of oxygen divided by the mass of the entire molecule, FeTiO3. Now, we'd have to multiply by 100 as well, so there'd be a times 100 here for each of these, since that's basically the definition of a percent, is that it's scaled relative to 100. Now, over here on the side, let's calculate the molar mass. That's what's going to have to go on the bottom here. Plus, we're going to want all of these individual pieces. So iron and titanium, I can just find on the periodic table. Iron is 55.85. Titanium is 47.88. And I've got 3 oxygens. Now, we already have seen oxygen a few times. It's 16.00. So you multiply that by 3, and that is 48.00. But all this is coming from the periodic table. So no, again, you've got to kind of be prepared to find what you can in the periodic table and use the periodic table when it's necessary. So I'm going to add these together to get the total here for the molar mass of the compound. Now, just right there, I have all the pieces that I need, because now I've got the mass of iron and the mass of the whole molecule. So for iron, this would be 55.85 divided by 151.73, and then that ratio multiplied by 100, that would be my percentage. So 55.85 divided by 151.73 times 100, and that would be 36.81%. Right, so that's the percent iron in that compound by mass. We can do the same thing for titanium, right? Just using the mass of titanium, that's 47.88 grams of titanium in 151.73 grams of the compound. So 47.88 divided by 151.73 times 100, 31.56%. And I'm using 4 sig figs here because of the number on top there of the fraction being 4 sig figs. Same for oxygen. Oxygen would be 48.00, total amount of oxygen in the compound, divided by 151.73 times 100. And multiply that by 100, and that is 31.64%. Right? So percent iron, percent titanium, percent oxygen in that particular sample. Now again, I said what I think is most important is the reverse, right? What we'll be able to do with this type of information. But this type of information can be useful as well, and the example would be the question here. If you know a sample contains 300 grams of titanium, how much of the compound would there be? Now, this might be a case of, right, I need 300 grams of titanium to build the product that I want, you know, to make the frame for my bicycle or something like that, although that would be a pretty small bicycle. So we want to figure out maybe how much of this ore we need to get and process in order to have 300 grams of titanium. Well, starting with 300 grams of titanium, right, these mass percents actually give us those 2 different pieces of information that we might want here. So if we want to cancel grams of titanium on the bottom and change that into grams of the entire compound on the top, right, that's kind of just upside down what we calculated up here, but that's also what's expressed here in the percent. So if you're given percent in a problem, keep that in mind. You've been given this ratio that would allow you to convert between the two. So 31.56, that would mean there's 31.56 grams of titanium in every 100 grams of that compound, and we can do that in one step there, that conversion. So 300 divided by 31.56 times 100 would be, so 4 significant figures in both of these, and that 100 in a percent is an exact number. So we've got 4 significant figures here, would be 950.6 grams of the original material is what we would need to have 300 grams of titanium. Now, you could do this without this information, right? We know how to go from grams to moles. You could figure out moles of titanium. You could figure out the ratio, how many moles of titanium are in a mole of the compound. That would get you moles of the compound. Then you could use the molar mass of the compound to get back to how many grams of the compound there are. Quite a few more steps, right? And in fact, once we figured out the molar mass, all right, we would have all those pieces of information. But much more convenient if you recognize that relationship in terms of mass percents. So what we'll do on the next page is figure out how to do this backwards. Start with these and get some information about molecular formula.